Can we continue, right? Yes. Okay. So let me briefly remind what we did last time. Actually, we did not do much. So last time I proved the theorem of Dirichlet approximation theorem. That alpha is a real number, and then there exists non-zero Q such that alpha minus P over Q is this, and and as a consequence that this inequality has this and actually right like this and this is right. Yes, and the corollary that the inequality this has infinitely many solutions in integers Q non-zero. So from this I deduced the theorems about solubility of Diophine equations of low degree. Of degree 1 and 2. So 1 is equation of the form x plus dy equal to 1, something like this, and the degree 2 it was Pell equation. Equations in this form. So this is what we did last time, and we stopped by just the theory of Pell equation. Now let's ask the question, okay, we want to go further. We want to consider, for instance, equations of degree 3. Good? Okay, so want to study x cubed minus d, say y cubed. So simplest equation of degree 3 is d, say not a cube. So that it's reducing. Good? And well, how we did here, we just applied Dirichlet approximation theorem to certain number, and then we found out that it somehow produced a solution, right? But if we want to do here, it will be Dirichlet approximation theorem won't be sufficient. So if apply, say here, if apply Dirichlet approximation theorem to here it was square root of this, so here must be cubic root of d. What we obtain? Obtain guys like cubic root of d, or well, x minus y is smaller than 1 over y squared. But then x cube minus dy cube, well, here it was smaller than constant. Here it was, so if we had square root of less than 1 over y squared, then we obtain that x squared minus dy squared was less than some constant depending on d. And this was sufficient to complete the theory, right? But here we do not get a constant, we get something growing, will be less than some constant depending on d times y. And the previous trick fails. So if we want to do something similar, we want to refine on the Dirichlet theorem, but is it possible to want to refine Dirichlet? good question. Is it possible to refine the theorem of Dirichlet? And well, the answer is unfortunately, or fortunately, I don't know, but the answer is no. In general, it is not possible to refine on the theorem of Dirichlet. And well, I'm now slightly breaking the chronological order. So I will prove now, I will remind now and probably prove a theorem which was established in the beginning of 20th century. So, theorem of Borel. So let lambda be a number, real number bigger than 2. And call alpha, real number, alpha, lambda, well, approximable if the theorem of Dirichlet can be refined with exponent lambda. So here, for instance, it's clear that we want to refine, if we can refine, say, with exponent 3 rather than 2, then a similar, something similar would work, yes? So if the inequality alpha, say, let us write it, okay, 1 over q to the power lambda, has infinitely many solutions. In with Q non zero. And then, theorem of Borel, which was proved slightly more than 100 years ago, tells, and well, also maybe I add one more, and call alpha simply well approximable if it is well approximable for some lambda. Bigger than that. Good. If with some exponent, the theorem of Dirichlet can be refined. Good. And now theorem of Borel tells that the set of well approximable real numbers is of Lebesgue measure 0. Yeah. The Baire category, it is big. From the sense of Baire category, it is big. But from the sense of Lebesgue measure, it is small. I think from the sense of Baire category, its complement is of this small Baire category. I already forget what is, which is big, which is small, second or first. But from the point of view, actually already Liouville numbers, big Baire category, so it's big. Okay, so the set of well approximable numbers is of Lebesgue measure 0. So the proof is rather easy. So it is not directly in the topic of our course, but the proof is easy and beautiful. So I will reproduce it. So the proof is based on what is called Borel-Cantel lemma. Of course, if you studied probability, then you have seen it. Borel-Cantel lemma. So assume that we have a measure space. Sorry?
No, you were saying that it's a lemma in analysis.
Yes.
Not probability.
Or maybe an analysis. Yes, well, depends. If you studied, yes, the theory of Lebesgue integral or whatever. So anyway, measure theory. So it's a measure space. So with measure denoted by mu, and so assume that A1, A2, etc., and etc., infinite sequence of measurable sets of finite measure, and we assume that the sum of the series is finite, so the series converges, so all of them are finite measure, and moreover the series converge. Then the tail set. What is the tail set? The tail set is the set of all points, which belong in the measure space, which belong to infinitely many guys of this. So which is what? So it will be what? It will be intersection for all n to infinity of unions from k from n to infinity ak. So it is tail set. The tail set is of measure 0. So the tail set again, it is guys who belong to infinitely many of A's. There is also, actually Borel-Cantel lemma has two statements in it. So there is also it's a sort of 0-1 statement. So if we have, and the second statement indeed belongs to probability, right? Yes. So if it is not just a measure space but a probability space, and the series diverges, and one assumes in addition that so these are, we can call them events, and the events are independent, then the tail set is of measure 1. This we don't need. I don't want to speak on this, so this is what is sufficient for us. Good. So then the proof is pretty obvious. Proof. So T is contained in the union for every n. And so the measure of T is bounded by the sum of but since they're series, converges, there exists, then for every epsilon, there exists n such that the sum is smaller than epsilon. And so we obtain that mu of t is smaller than epsilon for every epsilon. So it's very easy. And now how the theorem of Borel is proved. So for every q, so theorem of Borel, proof of the theorem of Borel. So we, of course, it is sufficient to prove that lambda measurable for some lambda, well approximable numbers in the interval 0, 1 form a set of measure 0. Why? So for fixed lambda, so we can fix lambda and we can also take elements from this interval, because if it is true for every lambda, then we can take a countable sequence of lambdas tending to 2, and all well approximable will be union of countably many sets like this. And again, here we can cover R, but countably many. So it's sufficient. Good. So now, for every Q, let Q be a natural number, and consider the following. Consider those guys which are well approximated by fractions with denominator Q on this interval. These are what? So we have the following. So 0. And now here until 1 over Q lambda. Then we have 1 over Q. And here 1 over Q minus 1 over Q lambda. And here 1 over Q plus 1 over Q lambda. And so on. Here again 2 over Q and take interval around, etc., etc., until, and at 1 we have 1, and so 1 minus 1 over Q lambda. And so we want to consider this set, etc., until here. Good. Set like this. So in symbols it will be what? It will be so call it AQ. It will be union from K to Q minus 1, K over Q minus 1 over Q lambda, K over Q plus 1 over Q lambda, and also two halves, half near 0 and half near 1, right? So, and also we have to add to this the interval 0, 1 over Q lambda, and the interval 1 minus 1 over Q lambda, 1. Now, what is the measure of AQ? What is the measure of AQ? The measure of AQ is, so we have Q minus 1 full intervals and 2 halves. So we have in total Q times full intervals. And each full interval is 2 over this. So the measure is Q times 2 over Q lambda. So 2 over Q lambda minus 1. Right? Good. And now what is alpha is lambda well approximable if it belongs to AQ for infinitely many Q. It's exactly the definition, right? If and only if alpha belongs to AQ for infinitely many Q. So the set of well approximable numbers, lambda well approximable numbers, is exactly the tail set, which is so union for Q from 1 to infinity. And here K I just don't very good. L from Q to, intersection here union AQ. Now what we know, what is so this is well approximable, lambda well approximable numbers. It is this set. And now what we know about the series, so mu of AQ, is the series, well, up to constant, q lambda minus 1. But lambda is bigger than 2, so lambda minus 1 is bigger than 1, so it is converges, because lambda minus 1 is bigger than 1, and well. So for almost all real numbers, Dirichlet theorem is something best possible that we can say. And this means that if we have some individual real number, it is there is no reason, unless we somehow specially construct it to be well approximable, there is no reason to assume that it is well approximable. Most probably it isn't. So most probably if we have some individual real number, then we cannot refine Dirichlet theorem for it. So we should abandon the idea of trying to refine Dirichlet theorem, say, for cubic irrationalities, for cubic root of D, or some other numbers. Well, as it very often happens in mathematics, and especially in number theory, if we have certain property which holds typically, it's usually easy to show that certain property holds typically, but very difficult to show that it holds for some individual objects. For instance, well, this property of being well approximable is a very good example for this. For instance, we know, so what we know that E is not well approximable. So for E, one cannot refine the theorem of Dirichlet. The proof is not so difficult because we know for E the continued fraction expansion, so it is it's relatively easy. See, one can find there is strange book of Leng, Introduction to the Theory of Diophine Approximations, or something like this, small book, and there is a proof there. So it's not difficult. On the contrary, pi already is a big mystery. We know that we cannot go with exponents something like about 4, but to approach to 2 is an open problem. I think it is a problem of Fields medal level, probably. So, Fields, I think, to show that pi, you cannot refine Dirichlet theorem for pi, is a problem of Fields medal level. So, well, I don't mean that. Well, I think that there are much easier ways to get Fields medal than to prove this. So one can show something about, I don't remember exactly, you see, one can show something like that one cannot go beyond the exponent 4 or 4 times, maybe 4.2 or some, I don't remember the exact one. There is still some world championship on this, and people continue to refine a little bit. So. But the numbers we're mainly interested are not E and pi, but the numbers we're interested in are algebraic numbers. What happens to algebraic numbers? So one should prove for algebraic numbers certain result which is in going to opposite direction to Dirichlet, that one cannot approximate algebraic numbers by real numbers too well. And the first result like this was the theorem of Liouville. So I now go chronologically back. Liouville did not know about the theorem of Borel because it was about some 65 years before, and actually 2 years after Dirichlet. And Dirichlet, remind, was 42. So theorem of Liouville is the following. Assume that alpha is an algebraic number. So Q bar, but not in Q. irrational algebraic number. And denoted by n, its degree. So the degree is at least 2, because it is irrational. Then for any rational number p over q, we have this inequality. Q to the n, exponent n. So one cannot approximate algebraic number better than with exponent equal to its degree. And in particular, if n is equal to 2, we obtain exactly what? Corollary. Algebraic numbers of degree 2 are badly approximable, are not well approximable. But even a stronger statement, we cannot put. So Dirichlet theorem, badly approximable means that we cannot refine. We cannot do Dirichlet theorem with some bigger exponent than 2. Here it's even stronger. Even with exponent 2, we cannot improve on this constant. So we cannot put here some function growing to 0. So it is even stronger statement. So algebraic numbers of degree 2 are badly approximable. Dirichlet cannot be refined for them. Again, the proof of this theorem is very, very easy. So today I have only easy theorems. Well, I think difficult theorems will probably start from the next. So next will be something much more serious. So, next lecture. So now the proof. So let f of x be the minimal polynomial of alpha over q. So the degree of f is n. And now let p over q. So then what can we write? We can write so f of x is x minus alpha times some other polynomial g of x. Right? Now what we, where is it? Oof. Now let's take p over q in the interval alpha minus 1, alpha plus 1. If p over q outside this interval, then we obviously have linear, right? We take it in this interval, and now let us estimate, so f of p over q. On the one hand, it cannot be 0. F is irreducible polynomial, and it has no rational roots, so it cannot be 0. And now, by the main theorem of number theory that I stated last time, it should have, it is a rational number, and its denominator is at most q to the power n, and numerator is at least 1, right? So by the main theorem of number theory, it is at least 1 over q to the n, right? Slow estimate. Now, upper estimate, it is bounded by alpha minus p over q times maximum of g of x, where x belongs to the interval. And this is some constant depending on alpha. Some constant depending on alpha, and we are done. So C will be 1 over C prime. And, well, it shows that, it does not show that, well, it shows that algebraic numbers of degree 2 are badly approximable. But well, we expect also from other algebraic numbers that they are badly approximable, but it does not show. It shows something weaker. But let us try to make use of at least what we have. So let us return to the equation x cube minus d, say, y cube equal to 1. And let us try to, if we cannot show that this equation has infinitely many solutions, let us try to show that this equation has finitely many solutions. So assume that square root of d is, cubic root of d is not lambda well approximate. So, which means that that for alpha minus, so cubic root of d minus y over, or x over y is bounded by some constant depending on y, or some constant depending on d. So means that we have this sort of inequality. Good. Then if we write down this x cube minus d y cube, then it is clear that this would imply some sort of inequality of the form c, some other constant c prime, y to the power 3 minus lambda. Good. And this means that if we manage to prove it, this for any lambda smaller than 3, then equation x cubed minus d y cubed equal to 1 or equal to some has finitely many solutions. So it cannot take certain value infinitely many times. This cubic form. Good. And but what Liouville theorem it gives us as this exactly with lambda equal to 3, so insufficient. Actually, one can ask a more general, consider a more general type of equation. This is a very special case of what is called the Diophine equation of Thue. So let us consider the Thue equation, probably one of the most interesting, most famous types of Diophine equations. What is this Thue equation? It is an equation of the following form, that f of xy be a homogeneous polynomial of degree n. So we write it as a0 x to the n. Okay, that will be y to n plus a1 y to n minus 1 x plus etc. plus a n x to the n. So homogeneous put in spelling. Do they spell it correctly? Homogeneous? I hope yes. Homogeneous polynomial of degree n, at least 3, and we assume that it is irreducible over Q. And also let b be some arbitrary integer. And then Thue equation is this equation. This is called Thue equation. And again, let alpha be a root of the corresponding polynomial. So which polynomial? Let alpha be a root of f of x1. Then alpha is algebraic of degree n. And assume that we manage to prove that alpha not lambda well approximable for some lambda smaller than n. Then it's easy to see that f of xy will be what? Will be at least some constant times say y to the power n minus lambda. It's easy to deduce because why? We can write f of xy as so if f of x1 is a what? n times x minus alpha 1, etc. x minus alpha n, where alpha 1 is say alpha, and then well, it's not really well what I say. Assume that any root, this is true for any root, not just for one individual, assume that this is true for any root of alpha. Then what we have? Then we have f of xy is what? Is y, absolute value y to the power n, and then alpha 1 minus x over y, alpha n minus x over y. And among these n terms, only one can be small because all the roots are distinct. So one can be small and the other are bounded from below by certain constant. And so say this is at least, and all the other are bounded by some constant, separated from 0 by some constant, and so it will be f of xy is at least some constant y to n minus lambda. And again, if we manage to do it, with lambda smaller than n, then Thue equation has finitely many solutions. Then has finitely many solutions. And again, Liouville theorem is insufficient for this. But any refinement of Liouville would suffice. And the same year as Borel work, such a refinement was obtained by Thue and Thue in the article, probably most important article on the theory of Diophine analysis, Thue's article 1909. And recently in Bordeaux we had a conference dedicated to the anniversary of this article. Formally, conference was dedicated to 150th anniversary of Thue, but the idea was to celebrate the anniversary of this article, and originally we wanted to have this conference in 2009. But 2009 we did not have funding, but for this year we did find some funding, so we did it. So Thue proved that if alpha is algebraic number of degree n, then alpha minus PQ is let me write. We always assume possible that Q is positive, so I will not write absolute value. Then we have this inequality. So let me write C of alpha and lambda for any lambda bigger than n over 2 plus 1. Very well, if for any PQ. If lambda is bigger than n over 2 plus 1. So one can refine theorem of Liouville by any exponent bigger than n over 2 plus 1. This was what was proved by Thue, and for n greater equal 3, this is better than Liouville. Because already so n over 2 plus 1 is strictly smaller than n. And the immediate consequence, the Thue equation has finite domain solutions. Has finite domain solutions. But there is a price that we have to pay. For this refinement, and so far, one can only very partially overcome this problem. Is that this constant C of alpha lambda is non-effective. There is absolutely no way to estimate it in terms of alpha and lambda, estimated explicitly in terms of alpha and lambda. And I will sketch a proof of the theorem of Thue. It will take us one additional lecture, but I think that it is very useful just to appreciate effective method. It must be useful to see first how non-effective method works, just what happens there, and why it is. It's not, you see, sometimes, things that non-effective is just something psychological. It's very difficult. One gets some complicated formula, but if one works hard enough, one can write it. It's not like this. It's simply no formula. It's, whatever complicated, we just cannot do it. Yes. And we will see why it is the case. Basically, the idea is that we need to study two approximations here. So there is no contradiction if there is one good approximation. One needs two good approximations to have a contradiction. And this means that there is no way of bounding this. We'll return to this point later. But well, still, Thue as a result, it was outstanding work. Actually, all subsequent work in Diophine approximations, all subsequent substantial work in Diophine approximations used tricks and ideas from this article that were first introduced by Thue. And it seems that for me at least, Thue's article just comes from nowhere. It is just, I'm not of course a specialist in history of mathematics, but I personally cannot trace it back. I just don't understand. So he was sort of genius. So David Masser told me that he can trace it back to some other work of Thue, but good. But still, well, it is not. It was not what we expect. So expect that algebraic numbers are not lambda well approximable for any lambda. So expect that instead of this, one should have just for any lambda bigger than 2. Good. So the inequality like holds for and lambda bigger than 2. Well, so evidently Thue's result was not best possible. And indeed, 20 years after, it was refined. It was refined by Siegel. In yet another extremely influential article. Actually, it was an article consisting of 2 parts. And Siegel proved that this can be done for lambda. Note that this is greater or equal to square root of n. Actually, Siegel had a slightly sharper result. It was something like lambda bigger than n over integral part of square root of n plus 1 and plus integral part of square root of n. And clearly that this number is strictly smaller than 2 square root of n, so 2 square root of n would do. Oh, sorry, it's not. So this number is strictly smaller than 2 square root of n. And Siegel, why Siegel? Actually, Siegel indeed he did not do the refinement just for the sake of refinement. It was important for Siegel to have this exponent growing slower than n. So it was important for Siegel to have this O small of n. And why it was important? Because he, again, like Thue, he applied his work to define equations, but well, Thue's application is easy. So we have seen that it's almost immediate from the theorem of Thue that Thue equation has finitely many solutions. Siegel proved a much more general result, which is called the theorem of Siegel on integral points. And it was a highly non-trivial application. In the same article, in the second part of the same article, on integral points. So what he proved? He considered arbitrary where f of xy in is just arbitrary polynomial irreducible over Q. Then it defines an algebraic curve. What? And assume that this is a curve of genus greater or equal 1, or of genus 0, but with at least 3 points of infinity. So we projectivize this curve, we obtain certain points at infinity and assume that there are at least 3. Then the equation, call it Z, has finitely many solutions and integers. So a curve of genus at least 1 or of genus 0 but with at least 3 points at infinity has only finitely many integral points. Of course, it is much more general. It's easy to see that Thue curve satisfies this solution. Actually, it is already at least genus 0, and also Thue curve has at least exactly n points at infinity. So by any of these criteria, so by any of these criteria it works. So it is much stronger result, and Siegel needed some really non-trivial argument to deduce this from his Diophine approximation theorem. Actually, he obtained a more general result by approximating algebraic numbers by other algebraic numbers, but from a fixed number field, so I don't speak on this. And he used some sort of covering argument, and for this covering argument, he indeed needed this O small. Something that went to infinity, and he needed that it doesn't go to infinity too quickly. So I don't think that I will prove in my course this theorem. Not that it is very difficult, but it is a bit outside the scope of this course, because so far, in general, no effective version of this theorem is known. And of course, Siegel's proof was non-effective. But I will probably prove it for curves of genus 0 and 1, where it is effective. And we will see how at least in partially this can be made effective. Good. Okay. So later it was refined by the theorem of Falsing's that if genus is at least 2, then even rational points are infinite, but this is even more non-effective, so we will not speak on this. Good. Okay, so I think it is a good point to make probably a break, some 5 minutes, good? I just continue this brief historical account. So what we're speaking is how, or which lambda we can have this sort of inequality. Q to the lambda, sorry. For which lambda, and Siegel showed that where alpha algebraic of degree n, and Siegel shows that it is for at least this. Now, there was some intermediate work, which is sometimes forgotten, but actually it was important work because some tools were developed, were used later independently by Gelfond and Dyson. It was not a joint work, it was independent work, something around 40s. I don't remember the exact years. 40s. Oh, it was looks like minor improvement, but it was important work from conceptual point of view. And finally, Roth in 55 obtained the long expected result that all algebraic numbers, for algebraic numbers, we cannot refine Dirichlet theorem. And you know that he got Fields medal for this. So, and I believe that, say, effective refinement of Theorem of Liouville, say, with exponent not depending on alpha, is more difficult for this. But Roth got Fields medal. Anyway, so what my further plan is the following. I will outline the proof, the initial argument of Thue, how it worked. And then I will say very briefly which new elements were introduced by Siegel, by Gelfond Dyson, and by Roth. So in particular, for instance, how Roth managed to get rid of dependence on the degree. Actually, it's very funny. One has to use here the law of big numbers in probability, and this exponent 2 is the inverse of the 1/2 which occurs in the law of big numbers. So the law of big numbers would say that if we throw a coin many times, then the number of faces will be about 1/2 of the whole number. And this 2 is the same 2, which is 1/2. Also, one can also interpret this 2, by the way, in a different way as a Euler characteristic of the sphere. It also has some reasons to be interpreted like this, and so on. But, okay. Return to this later. So this will be, it would be a sort of off-topic for this course because it is, as I say, effective. But as I say, I want to start from non-effective methods so that we can fully appreciate what effective methods give. And well, what was the main one of the main tools behind the proof of argument of Thue was what is called gap principle. Gap principle in Diophine approximations tells that good approximations to a real number are very, very sparse. Is it with S or with C? I will write this. Yes. And is it correct spelling? Yeah. So, well, I will prove some versions of this gap principle. It was not exactly what was used by Thue, but it is something very similar to what was used by Thue. Actually, Thue took two good approximations, and from one of them, which is smaller, he produces a third good approximation, and this third and the second, they are in conflict because of this gap principle. But now let's just see how it looks like in the pure case. So let's forget about algebraic numbers. So let again alpha be a real number. Now let C be a positive number, and let lambda be a number bigger than 2. Good? Now we say that P over Q is a C good approximation for alpha if we have the inequality C over Q squared. Good? And let us say that P over Q is lambda very good approximation if we have 1 over Q with a lambda. So simply good approximation is just when we put here some small constant. Very good approximation if is when we touch the exponent. Good? Now, proposition. So let alpha be a real number. And part A. Assume that P1 over Q1, P2 over Q2, etc. be sequence, infinite sequence of C good approximations. And we assume that they are indeed different, so that Pi over Qi is distant from Pj over Qj for I distinct from j, and that denominators grow. And C good approximations, and with C smaller than 1/2. So actually, I think that this restriction can be relaxed, but it is not really, that doesn't really matter. I just do not want to obtain the best possible result, but to show the principle. Then denominators grow exponentially. We have the inequality Qn e to some theta n, where theta is a positive number, well, depending on that. So if we have just good approximations with constants smaller than 1/2, then the denominators of this good approximation must grow very, very quickly, exponentially. So they're quite sparse. Now part B, same, but lambda very good approximation with lambda bigger than 2. Then Qn grow double exponential, even much weaker, much sparser. So we have Qn bigger than e to theta n. And it's quite easy to see. As I promised today, there will be no difficult proof, and this This is not an exception, it is an easy proof. Sorry?
This theta doesn't depend on lambda. What lambda is?
Probably it does, yes, it must depend on lambda, yes. And here also depends on C. Yes, sorry. Yeah, of course they must depend, yes. Actually, I believe that this theta is probably absolute. I believe that it should grow as quick as the Fibonacci numbers. One can show, but not with the argument I'm going to. But actually, one can show that good approximations grow as quick as Fibonacci numbers. So it is not really here. Here it is more or less absolute. Here I'm not sure. I think that here indeed should depend not on alpha, but rather actually not on alpha. Alpha is not, yes, actually it depends on here on C and here on lambda, yes. You're right. Lambda, but not on alpha. Alpha is not really good. So, proof A that P and Q and R over S be two C good approximations, distinct, and assume that say S is bigger than Q. Then what we have, if we take the difference, on the one hand, by the main theorem of number theory, it is this. On the other hand, it is bounded, so P over Q minus alpha and R over S minus alpha. So it is bounded by the constant over Q square plus the same constant over S square. Good. No, this is first. This is first, this is squared. And what we obtain an equality of the form. So if we have an equality, say like xy is smaller than c x squared plus y squared, but c is between like this, then clearly x and y cannot be too close to each other, right? Then and say x is bigger than y, then x must be bigger than, say, 1 plus some c prime y with c prime some positive number. Well, I let you calculate this c prime yourself. Easy here the condition. If it is exactly 1/2, then this is equality when they. Okay. So, and this means that for each new good approximation we have this. So it implies the proof for part A. Now for part B is even simpler. Even simpler because we have 1 over Qs is smaller than 1 over Q lambda plus 1 over S lambda, and so it is smaller than 2 over Q lambda, which means that S is bigger than Q to the power lambda minus 1 over 2. And clearly this implies double exponential. Since lambda minus 1 is bigger than 1, this implies double exponential growth for these guys. So we obtain this sparsity. So they are very, very sparse. And now how the argument of Thue was organized, it was the following. argument of Thue. So assume that we have, again, two good approximations. So P over Q and R over S. Say lambda very good approximations with some lambda. And with Q smaller than S. Then Thue produces yet another approximation P square over Q square, sorry, P prime over Q prime produces from using P over Q. And he's doing in the way that Q prime is of same order of magnitude that S, the denominator Q prime is of same order of magnitude as S. But P prime over Q prime is not R over S, it's different. And the most difficult part of the whole argument is just to ensure that this is not the same guy, that he does not obtain by accident the same guy. Actually, this is the most difficult part of the whole proof. And then using argument like before, like just before, gets a contradiction. And so this already implies why it is non-effective. Because if we have only one very good approximation, we do not get any contradiction. We still do prove finiteness, right? If we have only one very good approximation, then finiteness is okay. We're okay with finiteness, right? But there is no contradiction, which means that this very good approximation can be as good as, a priori, as good as it was. We know that we can just accommodate our constant C to take care about this guy, but we do not know how it would look like. To get a contradiction, we really need to have two guys. This is how it works. Now let us be a bit more detailed. So how I say how it is how he is producing. I said he produces this using this. How he is doing? He's doing it in the following way. Right? Let f of x, g of x be two polynomials in integers. And want f of x minus alpha g of x. It is again polynomial, but already with algebraic coefficients, right? And want this to have a very high order vanishing at alpha. Say like f of x minus alpha g of x. Look, x minus alpha to some big power, which power? Some number n times some other guy. Say h x. Now, if we obtain this, then what we would have? We would have that f of p over q minus alpha g of p over q will be very small, something like some that I don't want to some c over q to say lambda n. So of course I will be cheating here, but this is what would we expect, right? And if we denote so the polynomials, the degrees of the polynomials is bounded by some other number, say m, then what we obtain? We obtain that if we multiply it by so what would it be? And it would be that or alpha minus f of p over q over g of p over q will again be something like so. Let us for the moment. So it is of more or less same magnitude f of alpha if p over q is very close to alpha. So let us forget about the magnitude of this guy. It is of secondary importance. So what's of main importance is the denominator and numerator of this fraction. So it is again the some q over lambda n. But this can be written as some p prime over q prime, where q prime is around q to the power m, right? And what we obtain? We obtain that this will be some c to q prime to the power, say, lambda n over m. Now, which n over m? So the beta n over m is the beta n over m is the doing it correctly. Now let us see which to ensure that all it works. How can we make the numbers m and n? What can we do? So this new alpha of f of x minus alpha g of x is at least n, means that we have n linear equations or coefficients n linear equations, right? And actually, it is not n linear equations. Unfortunately, it is more, because this means what? This means this is an algebraic number in the field generated by alpha. So it is n linear equations, but with coefficients in the field. If we want coefficients over q, it will be this number of n times little n linear equations over q. Right? And variables, in variables, which variables are, which are coefficients of polynomials f and g. So we obtain n equations in 2m, around 2m variables, right? Well, actually 2m plus 2, but let us forget about this. very close. And to have a non-trivial solution, what we need that this bigger than to m. So m should be something like n over 2. Right? Oh, at least, sorry, small. So m should be about like this. Slightly bigger than this, good. So this quotient is will be something like 1 over n over 2. And now let us, if we managed to, so it will be. They make. No, I don't think that. Is there a mistake? And well, now it is probably a bit too late to continue. So I think that really with so next time we will see in details how it would work. So this is actually n over 2 in Thue is constant. And on the other hand, we will see that it will somehow interconnect with the other approximation, and we will see that when lambda is bigger than n over 2 plus 1, we will obtain this sort of contradiction. But I believe that now it doesn't really make sense to going any further because it is a long argument. So I prefer to continue it next time. So next time we meet on Tuesday, same time, 4:30. But only for 1 hour, not for 2 hours, right? And so what it will be? It will be next Tuesday. So today is 14th, so it will be 21st. Yes, 21st. Yes. Okay. So of course here I disregarded many things. So actually it is not simply linear algebra because, for instance, I totally disregarded that these polynomials can have some coefficients and these coefficients intervene and this intervention can be substantial. You see, I just spoke about only p over q, but actually, so we should control the coefficients of these polynomials and we should control also many other things, and the most important thing we should see that this new approximation that we construct it will not be the same as the other guy. So it must be different, and this is the most unpleasant thing is the whole argument. So next time we will go into all this. Good.